Welcome to chapter 11, module 11. And in this module, in this chapter, we're going to learn about variances. So in the previous chapter, we were learning about means and differences between means. And so now we're going to see how we could get some information out of variances. And if you remember, we have the mean, and then we also have variance and standard deviation. But both those measures are important. So both a measure of central tendency, so here, would be the mean, and then also a measure of dispersion. Is our data really close to the mean, or is it dispersed? Is it dispersed from the mean, right? Close to the mean or dispersed from the mean? And so to illustrate this, if we had like 4 data points and we had like 8 and 10 and 10 and 12, our mean would be 10 and our data would be closely grouped to that mean. But if we had like 2 and like 18, and then like, let's say 2 and 14 would be 16, and then 18, and then like another, that would be 20, 36, and then another 4. So we had 2, 4, 16, and 18. Our data would be more dispersed, but our mean would still be 10. If we had 2, 4, 16, and 18, right, that would still be a mean of 10, but our data has much more dispersion, much more variance. And so we want to know not only a measure of central tendency, but also of our variance, right? How dispersed is our data? And if you remember variance, if we look at those symbols, let me bring that up. So here are those symbols. And if you remember, we have the mean, and this is what the mean looks like, how we represent it for a sample, it's X bar, and this is how we represent it for a population, it's mu. And then we have variance, which is S squared or sigma squared for a sample or a population. And then we have standard deviation, which is just S. It's the square root of variance for a sample, or it's sigma, the square root of variance for a population, right? So that's how those are all connected. So now we're going to learn a little bit about inferences about population variances. And so an inference, statistical inference, inferential statistics is where we have a population and we do a sample. And based upon that sample, we can make inferences about the population. And we're going to do that for variance. So inferences about a population variance is what we're going to see. We're also going to see inferences about 2 populations variances. So single population variance and 2 population variances. And a variance can provide important decision-making information. Consider the production process of filling containers with a liquid detergent product, right? So the mean might be, in the book, they use an example, and the mean is, let me find it, hold on one second. So in the book, they give the example of filling to 16 ounces. So if 16 ounces is our mean, we could still have very dispersed data, right, with a large variance, a large standard deviation, or we could have narrowly dispersed data where it's really clustered tightly around the mean. And so we want to make sure that, for a company, we're saying you're going to get 16 ounces, that we're monitoring that and ensuring that we're not giving people too much because that costs us money. But we're also, not shortchanging them because that's going to be bad for our brand reliability and our brand image. So variance can provide important decision-making information. Consider the production process of filling containers with a liquid detergent. The mean filling weight is important, but so too is the variance of the filling weights. By selecting a sample of containers, we can compute a sample variance for the amount of detergent placed in the container, and then based upon that sample, we can make inferences about the population variance. If the sample variance is excessive, overfilling and underfilling may be occurring even though the mean is correct. And so we're going to work with this in relation to both interval estimation and hypothesis testing. And the first one we're going to look at in this video is interval estimation. And I need a drink of water. I'll be right back. Hold on. I'm back. All right, so inferences about a population variance is chi-square, and chi-square distribution is the sum of squared standardized normal. So we're going to use a new type of table of distribution for figuring out, like our distribution and our percentages and whether we reject or do not reject, and it's going to be chi-square. So we've used like the Z table. We've used the T table. There's also an F table, and there's also chi-square. And so all these are just used in different situations. And again, in statistics, we're learning about different tools for different situations. And so when we come across a situation that warrants and merits a certain tool, we use that tool. And you've heard that analogy before. So let me just bring these up for a second so you can get your eye on them. Hold on. So here is the Z table, which is the first one we worked with. And if you remember this one, let me just bring it over for you. That's right here. That's a Z table, right? And it's a type of distribution, normal distribution. And we use that in certain situations. Then we have the T table. And here's another one that we use in certain situations, and that's the T table. And then we're also going to have chi-square, right? We're going to have chi right here. And so here's that one, which is right there. And it's the chi-square distribution, the T distribution, and the normal, standard normal distribution, the Z table, the T table, T distribution, and the chi-square distribution right here. And so we'll be working with each of those, and I'll just leave those up so we could come back to them when we're working with them. But the first thing, since we're learning about chi-square, it's a new table. I thought I'd just go to ChatGPT and ask about it. So I said, please explain chi-square to me. Thank you. And so it went through all of this, and you could pause the video here and you could read that. And these are ways we'll be using chi in the future. So it's useful to know. So go ahead and read through that and pause the video and read through it. And then you could also pause the video right here and you could read through all of that, which is the rest of the description. And then I uploaded some slides from the presentation that we're working on right here. I uploaded this slide right here. And then I also uploaded this slide right here. And then I also uploaded this slide right here. And I said, what about using chi-square for interval estimation like in the attached slides? Please show how to solve and explain that example. And so it gave an explanation right here. And again, if you want to see that example, there it is. You could read that and pause the video, read it. And so then it solved that problem right here, and it got the same answer as the textbook. So you could pause the video here and you could read through that. And then you could also pause the video right here and you could read through the rest of it. And that provides a really good explanation of what we're going to see in this video. So I highly recommend that you pause the video, go back a little bit and read through those, because that's going to start to give you a heads up about using this stuff. So to learn about chi-square, is the sum of squared standardized normal random variables such as z, all that, and so on. The chi-square distribution is based on sampling from a normal population. The sampling distribution of, and so sampling distribution n minus 1, and this is sample variance divided by population variance, has a chi-square distribution whenever a simple random sample of size n is selected from a normal population. We can use the chi-square distribution to develop interval estimates and conduct hypothesis tests about a population variance. So out of all of this, this is like the one bullet point that really stands out to me. The rest of this stuff is like, informative. It's, but it's a little bit lost to me. So maybe we'll come back to this and see if it makes sense to us at the end. And again, I really like to record these videos and show you the way I figure stuff out, because I think that's as useful as anything, because we figure it out together and we make sense of it together. And then you also see the process of how to actually figure it out. And so here, are some samples of like what chi-square can look like. And the more degrees of freedom you have, you can see the more it starts to approximate a normal distribution, more of a bell curve here. And then this formula right here, which we saw in the previous one, which is right here, the sampling distribution. So these are the, I imagine these are the formula, these are the graphs that are shaped by this formula. And n minus 1 here would be your degrees of freedom. And so that gives you a sense of like a chi-square distribution whenever a simple random sample of size n is selected from a normal population. And then the more degrees of freedom, the bigger your sample, the more it's going to approximate a normal distribution, which really resonates with what we've been learning, that the larger your sample size, 30 or more is kind of that magic number, the more you're going to start to get to a normal distribution. And so here is a graph of like, chi being used, chi-square being used, and we'll see this in action when we start doing ours. So we'll use this notation to denote the value of the chi-square distribution that provides an area of alpha to the right of the stated, chi alpha squared value. And so this is the area to the right. So here's the area to the right. chi-square 0.025, and that will be this area over to the right. And if we look at our chi-square table, so I'm just going to bring that up, and actually I'll get rid of this here, and I'll get rid of this here, and I'll just put this one right here. If we look at our chi-square table, and you have to get pretty close to this and make it kind of big, and maybe I'll put it over on this side just so we could have it larger and still see some of this. But here we're looking at 95 of the possible values, so it's like in 0.025 out to the tail. So here's the area of probability, and if we have 0.025, we have degrees of freedom here. And in this image, we aren't really told what the degrees of freedom are, but if it was the same as, and wasn't there, 10 degrees of freedom is right there is where we saw degrees of freedom before. And I'm just looking through here to see if we have any degrees of freedom. And we do up here where it's 20, so our degrees of freedom will be 19. And so we'll just see if these numbers correspond to 19. So if we came down to 19 degrees of freedom right there, 19, which is just your sample size, which is 20 minus 1. And we go to where we have 0.025 in the tail. So at 19, and we come over here to 0.025 in the tail, which is right there, right? So 0.025, that gives us 32.852 would be our chi-square value. And at this point, we have 0.025, or 2.5% of our data is out to the right. And then over here, if we wanted to see what our 2.5% of our data between here and there is, right, we would look for 97.5. Because the way chi works, it's from this point to the right. So at 97.5% of our data, which is right here, right, at 19, we're going to have 8.907. And so there we have 8.907. And let me just make this a little bit smaller now that we aren't needing it quite so precisely, right? But here at 19, we have 8.907, which means 97.5% of our data is from here to the right. And that would give us 0.025 in this tail. So at this point here, 8.907, chi-square value of that. We've got 2.5% of our data here and 97.5% of our data from here to the right. And here, chi-square of 32.852, we have 2.5% of our data from here to the right. And that means that, between these two, if we're doing an interval estimate, is where 95% of our data is. So that's kind of like the idea, okay? Between those 2 points, this one and this one, is where 95% of our data is. And so we'll use that notation to denote the value of chi-square distribution that provides an area of alpha to the right of the stated value. So here's an area to the right, and we saw that in action. For example, there's a 95% probability of obtaining a chi-square value such that, and here is this kind of idea that we could do an interval estimation, which is kind of what this first part is looking at. We can do an interval estimation of variance from a sample to provide an inference about the population variance, right? We could do an interval estimation using this formula here. Well, that formula is mathematically derived in the textbook. It shows you how they get to that. And so here's an interval estimation of population variance. So that's population variance. And then here we have these degrees of freedom. We have our sample standard, our sample variance. And then we have this alpha bit down here, right? So if, this is 0.025, then that will be 1 minus 0.025, or 97.5, and that's half of it here. So we had 5%, so we have 2.5% here and 2.5% here, where chi-square values are based on a chi-square distribution with n minus 1 degrees of freedom, and where 1 minus alpha is the confidence coefficient. So just going back up here and looking at our terminology, our confidence coefficient is the confidence level, right? It's 95% confidence level, confidence coefficient, 1 minus alpha. So alpha is really also the level of significance, right? It's the 0.05 would be our alpha. Level of significance is our alpha. And so 1 minus alpha, 1 minus those tails, right, is our confidence level or our confidence coefficient. So that's all terminology. It's a little bit of a terminology soup, which is why we keep coming back to that just to make sure we're square on it. You can pause the video right here and read it. All right, so that's that slide. And then here and then we could also estimate the standard deviation. So if this is the variance, if we just take a square root of everything, we get the standard deviation. And that goes back to what we already know, which is, where's my Finder? Finder. And Finder downloads statistics. What goes back to what we already know, which is this right here. I mean, you could see it this way. Let's see if I could get over there. Where is my mouse? There it is. You can see it this way, and you could also see it this way. And so let me bring this one over. Uno momento, right? Where you have your variance and standard deviation, and your standard deviation is simply the square root of your variance. And you could also see that right here, right? That your standard deviation is the square root of your variance. So that's that right there. And likewise here, right, we could go from our variance to our standard deviation by just taking the square root. So just connecting the dots here for you. So there's a 1 minus alpha probability. So like, alpha is 5%, and that 5% is our level of significance, and 1 minus alpha, 1 minus that is going to be our confidence level or confidence coefficient. So there's a 1 minus alpha probability of obtaining a chi-square value such that, it's between these two. Substituting this for, which is the chi-square distribution, right? Like this, if we look at what is chi-square, it's this formula here. It's right there. And we also see that here, the sampling distribution of this has a chi-square distribution, right? So if we, here in the book, when they derive this formula, they're saying, hey, instead of just putting chi-square here, we could put that here, where we sample variance, divide by population variance, and multiply it by n-1 degrees of freedom. So they substitute for this value that, which is the chi-square distribution, and then they solve for this, and they get this value here. So that kind of makes sense, like if we're going from here to here to get our 95%, the level, right? Here we have the x chi-square 0.975 and chi-square 0.025. So chi-square 0.975 and chi-square 0.025, right? Those will be the two values, and our 95% is going to be in the middle. Our chi-square is there in the middle, so we put in what chi-square is, and we solve for variance, and we get this, and then that becomes the formula. And so here's how the book talks about it, just in case you didn't read that page. And I'm just going to make this larger for a second so you could see that. And I'll wait for this to exit full screen notice to go away. But you could see there and read how they basically derive that formula. And it's pretty much what I just explained to you right here in that slide. So now we have a sample problem. It's the liquid detergent problem, example, whatever you want to call it. The filling mechanism for the process of filling liquid detergent product in a container is adjusted such that mean filling weight is 16 ounces per container. So that's our mean. A sample of 20 containers was taken to test this. If the sample variance is modest, the production process will be continued. If the sample variance is excessive, the filling mechanism will be readjusted to reduce the filling variance. The sample variance for the filling quantities is found to be that. Okay, that's our sample variance. So now, theoretically, we could take that with our sample variance, and I'm just going to open this up, and so we could do a side-by-side here. And I'll pull this out and make this go over here. And like that, we'll be fine. And then I'll bring this one over, and I'll bring it over here. And that will be fine. We'll just have one that's bigger. And so based upon that, we could probably start to put stuff in here because we know our n, we know our sample variance, right? And now all we need is this information down here, and we'll know, we'll have this formula pretty much solved. And so select the values from the chi-square distribution table for 19 degrees of freedom, and alpha is 0.05. So at 19, we've got 8.907, and then we also have 32.852. And that's exactly what we got here. 8.907 and 32.852, that's what we were already seeing. And so you put here 32.852 and here 8.907, because that corresponds, ladies and gentlemen, that corresponds to this formula here, right? So that's alpha divided by 2, and that alpha divided by 2 will be our 0.025, so that's 2.5%. And this will be the 2.5% at the other end. Quite frankly, I look at that and I'm kind of like, I'm not sure how you get to that. Like, what is 1 minus 0.025 is 97. but it's really alpha divided by 2. So your alpha is 5%. So you got 2.5% in each tail. This is going to be the upper 2.5%, right? So that's going to be your alpha 0.025. You can see it right there. And this is going to be your lower 2.5%. And since you go from here forward, it's going to be 0.975. And so to get to 0.975, it's 1 minus 0.025. That makes sense. That just totally made sense. I was thinking 1 minus alpha divided by 2, but it's alpha divided by 2, which is 0.05 divided by 2, and then 1 minus that 0.025, right? And this one's just 0.025. Totally makes sense. And so you put those numbers in, you get this. And a 95% confidence interval for the population variance is given by, so 95% confidence interval for the population variance is given by this. And taking the square root of these provides a 95% confidence interval for the population standard deviation. And so we could say with 95% confidence that, our variance is going to be between these two, and standard deviation is going to be between these two. And this is an error, by the way. And so to fix this error, I'm just seeing it, is like we need to do this. I'm going to grab a little box and I'm going to put this here. I'm going to go up like that. And then I'm going to go up here to the fill and I'm going to make it this color, which is just like white. And I'm going to do a border. I'm going to do transparent. And now that's correct, right? Because there's no, this is standard deviation. It's not variance. Variance is that. This is standard deviation. So the book makes mistakes. It's good to see it. And just comparing, like our confidence interval with what we came up with. So our sample variance is 0.025, right? As our sample variance, 0.0025. So we're between 0.03 and 0.07. And, that's dealing in ounces there. So that's how you do that. And you can apply this to the problems, and it's pretty cut and paste. Meaning that you just take this formula, right? You just take this formula whenever you want to kind of do an interval estimation on population variance using sample variance. You just take this formula here and you plug in the numbers and you get the result. And again, those numbers that are plugged in were derived by looking at, and let me see if I still have that open, by looking at this chi-square table, right? And looking at what is our confidence interval. It's between 97.5 and 0.025, 95% confidence with 19 degrees of freedom. And we get those chi-square values there, and those are the ones that go down in the denominator. All right, hey, it's statistics. Learning a bunch of different tools for a bunch of different situations. And in the next one, we'll see yet even more. See you in the next video.